Welcome to this video. In this video, we will be studying ICMP, the Internet Control Message Protocol. Now, the Internet Protocol V4 as such does not do any error reporting or error correction. So many things can go wrong, when you send an IP packet from a source to the destination and the IP packet goes through all of these routers in between, and many things can go wrong. So what if the router has to throw away a packet because it cannot find a route to the final destination, or because there is a TTL field in the IP packet, right? And if it becomes zero, so when a packet comes in, the router decrements the TTL by 1 and checks if it is zero. If it is zero, it has to discard the packet. Or the destination host, right, when it is waiting for all the different fragments of an IP packet to come. Now, IP packets can get fragmented, and it is not necessary that all the fragments reach the destination. And if it does not receive all the fragments, what does it do within a time limit? It cannot wait forever to get all the fragments. And so these are just three examples of what bad things can happen with IP packets. And IP packets go through a connectionless channel, right? So there is no connection made while sending IP packets. You just put a destination IP address and send the IP packets. So these are the bad things that can happen while using Internet Protocol. And the protocol itself has no way to tackle these things when they happen. It doesn't even report these errors. The protocol itself has no way to report these errors to the source host. The source computer which has sent these packets need to know what happened to its packets. And these packets can get dropped because of various reasons, and it is not going to know as such using plain IP. Also, there are no host and management queries capabilities in IP. As in, can IP help you know if a router or a host is alive? If I want to know if google.com server is up, how do I know? Can I use just plain IP as such to know if google.com is alive or if the server is down? So you as a network administrator need to have ways in which you can tackle these problems, and that is where ICMP comes into the picture. Now, there are two kinds of ICMP messages. We have error reporting messages when something bad happens. So wherever that bad event happens, that unfortunate event happens, if the packet gets dropped or something like that happens, from that point onwards, we send an ICMP error reporting message to the source of the IP packet, telling that, a particular problem has happened so that they can do something about it. At least they'll come to know. Okay, so those are error reporting messages. We also have query messages, in which you can do echoes. You send a packet and the packet is kind of bounced back to you. You send a packet, an echo request, and you get a reply from the destination, right? So those are echoes, and you can do that as a means of querying if a host is alive. Like google.com, you can send an echo request and it comes back with echo reply, and then you know that, okay, because the reply has come, that means google.com must be alive. And we also have timestamp request and reply, and we will look at these things in details in the next slide. Similarly, for error reporting messages, we have destination unreachable. So this is a broad type, right? And this type goes here. Then the destination might be unreachable because of various reasons. And there are many reasons why the destination might be unreachable. And to be very specific about what is the cause for the destination to be unreachable, we have different codes for a given type. So if the type is 03, yes, broadly we know the destination is unreachable, but to be very specific to why the destination is unreachable, you need codes for that. And it's called a checksum. And then you have the rest of the header, which is not important at this point of time for you to know. And any auxiliary information, which we will see what kind of information we store in these data sections, it's stored in this section. And then this thing becomes your ICMP packet. And ICMP uses IP. ICMP uses the Internet Protocol to be able to send its messages. For example, if your original IP packet gets dropped, so we create an error reporting message, an error reporting ICMP packet, fill in the type, code, checksum, all the important data in the data section. And then we take this packet and we will put this inside another IP packet whose source is going to be the point where the error happened, the bad event happened. The destination is going to be the origination point of the original packet, the packet which got dropped, right? It must have a source, and this ICMP packet has to go to that source. So the destination of this ICMP holding IP packet will be that IP address, the source of the original packet, because that source needs to know that one of its packets got dropped. Then you also have all different kinds of error reporting messages, which we will take a deeper look at. So before we go take a look at the different types of error reporting and query messages of ICMP, let's see how is ICMP kept as simple as possible. We want this protocol to be as simple as possible, because if it is complicated, then we can have lots of ICMP messages flooding around on the internet. As such, there is a problem with packets going, and that is why ICMP packets are getting generated. And if we have lots of ICMP packets, then managing so many packets is going to be a huge headache. If there is a problem already, let's keep the management messages to be as small a number as possible. That's why no ICMP error message will be generated if special addresses like the loopback address, anything of the form 127001, these kinds of addresses are loopback addresses, a local host. So if these addresses are involved in your IP packets, then no matter what happens to those IP packets, ICMP error messages will not be generated. Or if you have multicast addresses, okay, class D addresses are multicast addresses, and if those addresses are involved, then we will not have ICMP error message reporting. And no ICMP error message will be generated in response to a datagram carrying an ICMP error message. So your initial packet, right? So let me just make an IP packet here, and this IP packet gets dropped for some reason. And whoever is the router that is responsible for this packet getting dropped, this is going to send an ICMP message back to the source, right? The source sends the IP packet, it gets dropped. So the router, which is responsible for the packet getting dropped, sends an ICMP packet back to the source. Now, if this ICMP packet gets dropped somewhere in between, then we will not have another ICMP packet which is going towards the router saying that, okay, you send this ICMP packet, that packet itself got dropped. That is why I'm sending another ICMP packet to you. So then these packets will go back and forth, and that does not happen. And no ICMP error message will be generated if an IP datagram is fragmented, and that fragment is not the first fragment. So if you take a big IP packet and if it is fragmented like this, so for all of these fragments, if they get lost or dropped or for whatever reason, ICMP error messages will not be generated. They will only be generated if something bad happens to the first fragment out of them. So all ICMP error messages have a data section, and we saw that in the previous slide, and that includes the IP header of the original datagram. So you have an IP packet that is coming from the source, and it gets dropped somewhere, and we create an ICMP packet. That ICMP packet has a data section. So what we do is this original IP packet's header is stored in that data section. Okay, so that important information from that packet, who was the source, who was the destination, what was the TTL, all that information which might be required for debugging, to figure out, to do more investigation as to why the packet got dropped, all that information is stored in the data section of the ICMP error message. Also, the first 8 bytes of the datagram is also stored. So usually the first 8 bytes of the datagram, this is the payload, right? So the first 8 bytes of the IP packet usually will contain some of the header information from UDP and TCP. So it's usually UDP or TCP that sends data to IP, and the source port, destination port, all of that information is usually found in the first 8 bytes of both TCP and UDP packets, right? So that information will be present in the first 8 bytes of the IP packets payload. So not only is the header of the IP packet which gets dropped put into the data section of the ICMP error message, but also the first 8 bytes of the IP packets payload, which is the first 8 bytes of maybe TCP or UDP's header, because we have the transport layer packet going inside the network layer IP packet, right? So even that information is stored so that this information can be used by the source to figure out what wrong or bad things happened at the router which ended up dropping the packet. Okay, now let's take a look at the different kinds of error reporting messages that ICMP supports. The most widely used is the destination unreachable. Its type is 3, and this has different codes from 0 to 15, to be very specific about what actually caused the destination from being unreachable. And that's one kind. And the other kind is type 4, which is source quench. And this happens when there is congestion in the network. And because of that, if the router's buffers are full, a packet will get dropped. And if that happens, that router will send a source quench message to the source, saying that they need to slow down and not send packets as fast as they are sending. This is possible in TCP because TCP does some kind of flow control and congestion control, but IP, the Internet Protocol, it does not do that. So this is kind of helpful in getting some kind of semblance of congestion control in IP. Type 5 is a redirection message. This happens when you send a packet to a router for forwarding and the router figures out that it is the wrong router to be handling that packet. This happens when your default gateway, the default router in your configuration, is not configured properly. So you will end up sending the packet to the wrong router. The router will forward it to the correct router, but it will also send a redirection message back to the source saying that, well, you need to correct the default gateway configured on your host so that next time around you end up sending it to the correct router instead of me. So we know that IP packets have a TTL, the time to live, and when that becomes 0, then the datagram is not forwarded anymore. It is dropped. And so those kinds of messages are type 11 error reporting messages in ICMP, and we call them as time exceeded messages, right? And if a packet gets dropped because of that reason, because of TTL becoming 0, then the code is also 0. Like the type is 11 and the code is 0, right? This combination tells us that the TTL has become 0, and that is why we're dropping the packet. And there is another time exceeded message with code 1. Here the type is 11, but the code is 1. And this happens when within a predefined period of time, all the fragments of an IP packet, if the packet has gotten fragmented somewhere, and the reassembly happens where? It happens at the destination. But the destination is not going to wait indefinitely for all the packets to come. It is going to wait for a predefined amount of time. And if it is not able to get all the fragments of that big IP packet within that amount of time, it is going to send a time exceeded message, which is the same type as the TTL one, type 11, but the code here is going to be 1, so that the source knows that, okay, well, my packet was big. Well, I cannot do much about that, but somehow all the fragments did not reach in time at the destination. The last kind that we are going to discuss, there are lots of different types, but for the purposes of your syllabus, we're going to discuss only this much. A parameter problem message type 12 is sent out when there is a problem in the header of the datagram, or some options are missing or cannot be interpreted, right? So if the header of an IP packet, if there is a problem in that, things can go wrong. For example, the checksum may not match, or if some corruption has happened in the header, and if that is caught somewhere, then a parameter problem message is sent to the source saying that there is something wrong with the header of the IP packet. And there the type is 12 and the code is 0. But if there are options in IP packets, and we know at the very end you can have a variable length of options in IP packets. And if those options are missing for some reason, someone was expecting some options, if those are missing, or there are options which someone is not able to interpret what is supposed to be done about those options, then we send a type 12 message with the code 1 back to the source. Now let's take a look at different kinds of query messages. So we have an echo request of type 8 and echo reply whose type is 0. And these are pairs of messages. For one request, there is going to be one reply. And using this, you can figure out the liveliness of another host or another router. So a host or a router sends a echo request, and if wherever that request is sent to, if that host or router is alive, then it is supposed to respond with an echo reply message. And you will come to know that, okay, I got a reply. That means the host or router must be alive. Okay, the other one that we're going to study is type 13 timestamp request, and the corresponding reply type 14 as the timestamp reply. And these are also pairs of messages, and you can figure out the RTT between two devices. The round trip time between two devices can be measured using these timestamp request and reply messages. So the request message is going to the destination, and when it is created, it contains a 32-bit number, which is the time the message is sent, right? When you send a message, the exact time at that point of time is noted in this 32-bit number and sent as the timestamp request. When the destination gets this request, it sends that original number, that original number which was put into the request by the sender when the message was created and sent at the sender. That number is there, right there. So that is resent, bounced back to the sender by the receiver, but it also sends two new numbers. Now the reply has got three numbers. One is the original number in the request, which is just copied and sent back in the reply. It adds two new numbers. It is, the first number is the time the request was received and the time the response was sent. So with these three numbers, the sender, when the timestamp reply reaches the sender can figure out the round trip time, how much time it took for the packet to go and for the reply to come back. And for this to be possible, you need to have a common time zone. So if we choose the universal time, the UTC, as the time zone which is being used for all of these senders and receivers, then the sender can figure out not only the round trip time, but also the one-way time, because it knows when it sends the packet, that's the first number. The second number tells us when the packet reached. And the third number tells us when the reply was sent, right? So with all of this information, you can figure out not only the RTT, but also the one-way delay. You must have heard about the ping tool. So if you want to figure out if something is alive, some host is alive, and you also want to find out how much is the RTT, the time it takes for the data to go and for it to come back, right? So you use the ping utility. Now that uses ICMP. So it sends type 8 code 0 messages. Those are echo requests. And when those requests reach the destination then sends out echo replies, which are type 0 code 0 messages. Here the codes remain 0, whereas for the echo request, the type is 8. And for the echo reply, the type is 0. So what does ping do is that when it creates these echo requests and sends them towards the destination, it also puts a sequence number inside that. And when the reply for the same sequence number comes back, it is able to tell you the time it took for the packet to go and come back. And how does it do that? Well, it inserts the sending time in the data section of the message. When the packet arrives, it knows the arrival time, right? When it's sending the request, it puts the time instance in the data section of the message. When the reply comes, it carries that, it sends a copy of the data section, and when the reply comes, the sender also knows that, okay, when the reply came, it can subtract the two numbers and it can figure out the round trip time for you. And this is an example of the ping utility working, and you can try this on your computer also. This is the last thing that we will discuss about ICMP, and this is very, very interesting. So pay a lot of attention while you are hearing or trying to understand this. So traceroute is a tool that you can use to figure out the set of routers between you and the destinations. When a packet is sent out from your computer to a destination, there can be a bunch of routers in between, which there usually are. And if you want to know the host names and the IP addresses of all the routers, and you also want to know the host name and the IP address of the destination also, so you can use the traceroute command. So it works using two different kinds of ICMP messages. It uses time exceeded and destination unreachable messages. So what we do is we send a UDP packet, okay, and the UDP packet is created by the traceroute program, and the packet as such does not have much. The traceroute packet uses a port number that is not available at the destination, and you will know why this is important. It is very important that the port number that the UDP packet uses as the destination port number is not actually available. It is not actually open at the destination. The source here generates n plus 1 messages. Okay, so here, and what is the value of n? N is the number of routers in between. So here it is going to be 1, 2, 3. So it will generate n plus 1 messages. So it will generate 4 messages. So the first 3 messages will be discarded by the 3 routers in this sequence, and the last message, the 4th message, will be discarded by this. We want these messages to be discarded. That is why there is no traceroute server. There is only one client which creates a UDP packet, puts that packet inside an IP packet and sends it. Whatever it sends, those packets have to be discarded by the routers, and the last packet has to be discarded by the destination. Only when they are discarded will these time exceeded and destination unreachable ICMP error reporting messages be generated, and they will be sent towards the source. And from that we can know who discarded the packet and what is its host name and IP address, right? So very cleverly, what do we do? For the very first message, we set the TTL in the IP packet to be 1. So when that packet reaches the first router, this router decrements the TTL by 1, the TTL becomes 0, so the packet is dropped. So it is going to send a time exceeded error reporting ICMP message back to the source. And inside the message, you will be able to find the host name of the router, and that information can be found in the data section of the message, and the source address is going to be the IP address of this router, right? Because this ICMP message is going to be put inside an IP packet and sent to the source, and the IP packet will have a source, and that source IP address is going to be the IP address of this router. Okay, now we will send another traceroute message, traceroute UDP message put inside an IP packet whose TTL is 2. So when that packet reaches the first router here, it will be decremented by 1. Now the TTL is 1. So it will not be dropped. It will be sent to this router here. Now this router is going to set it to 0 and it will drop the packet. It will send another time exceeded ICMP error reporting packet back to the source, and the source will be able to figure out the host name from the data section, and from the source IP of the ICMP carrying IP packet, the error reporting packet will be there in some IP packet, and the source IP address of that IP packet is going to be the IP address of this router. So that information is now there. Then we will send another traceroute packet with a TTL of 3. Okay, and then it will cross this router. This router will only become 0 at this router. Yes, we have another time exceeded ICMP packet coming here. So now we know the details of this router also. So now what do? We send a different kind of message. We send a message deliberately where the destination port is not reachable. And this is something that I told you in the beginning. We have to send a message for the last message where the destination port is not available at this destination. So what will happen? This laptop is going to reject that packet. This destination is going to drop that packet, but it will not be sending a time exceeded ICMP message. It is going to send a destination unreachable ICMP message, right? And it's a different kind of message that you see here, right? It's a complete black message instead of the gray messages that were being used for time exceeded messages. And when this packet reaches the source, then the source knows that, okay, I have reached the destination, and from information present in the destination unreachable packet, you will be able to find out the host name of the destination, and we can also get its IP information. I hope you found ICMP very, very useful, because whenever you do ping or traceroute to figure out the route through which your IP packets go, it is ICMP which is actually used. And in this particular traceroute case, we do not have a traceroute server because these packets are supposed to be dropped either for TTL reasons or for the destination port not being reachable. These packets will actually never go back to the UDP, the transport layer, right? They will be dropped right at the network layer. They will be dropped at the network layer of this router, of this router, this router, and this host. It will never be going to the transport layers of any of these routers or the destination host, right? That's why we don't need a traceroute server. Only one client is enough. Thank you.